Let us now discuss another problem on finding area. The problem here is show by double integration that the area between the parabolas y square is equal to 4ax and x square is equal to 4ay is 16 by 3 a square or 16 a square by 3. We know that y square is equal to 4ax will be symmetric about the x-axis, x square is equal to 4ay will be symmetric about the y-axis. The portion common to them will be lying only in the first quadrant. The parabolas intersect at origin and also at 4a, 4a. We know that this portion or the shaded portion of the figure can be described in two ways. Let's now use one method where the region lies between two horizontal lines. One is y is equal to 0, another is y is equal to 4a, and it lies between two curves, one at the left and the other at the right, described by x is equal to y square by 4a and x is equal to 2 root ay. So the inequalities describing the region are 0 less than or equal to y less than or equal to 4a, y square by 4a less than or equal to x less than or equal to 2 root ay. Required area now becomes integral over the region R of dx dy or integral y is equal to 0 to 4a, integral x is equal to y square by 4a to 2 root ay of dx dy. Initially, we integrate with respect to x to get x. Substituting the limit, we get integral y is equal to 0 to 4a of 2 root ay minus y square by 4a dy. Here, root y, that means y to the power half. On integration, it becomes y to the power 3 by 2 by 3 by 2. So, on integration, you get 2 root a into y to the power 3 by 2 divided by 3 by 2 minus other term is y square. On integration, it becomes y cube by 3. So, we get y cube by 12a. Already 4a is there. Coming with multiplying with another 3, you get it 12a. To be evaluated at y is equal to 0 and 4a. So, substituting the limit, you get 32 a square by 3 minus 16 a square by 3, or it becomes 16 a square by 3. Let's discuss one more problem. This time we are considering a region in which we utilize polar coordinates to determine the area. The problem is find the area of one loop of the lemniscate r square is equal to a square cos 2 theta. We notice that in the lemniscate there will be two loops, one lying to the positive side of x-axis and another one lying on the negative side of the x-axis. Both will be exactly similar to one another, or will be the area of both the loops will be one and the same. Let us consider the loop shown in the figure lying in the first quadrant and fourth quadrant. Theta is equal to minus pi by 4 and plus pi by 4 will be asymptotes for it. And the required area, in the required area there will be two equal portions, one below the x-axis and the other above the x-axis. With this information, now let us describe the region of the lemniscate by inequalities. When we consider the upper half of the lemniscate, it can be described by 0 less than or equal to r less than or equal to a root cos 2 theta, 0 less than or equal to theta less than or equal to pi by 4. As we have noticed that the total area or the area of one loop of the lemniscate is twice that of the portion lying above the x-axis, we write required area as 2 times integral theta is equal to 0 to pi by 4, integral r is equal to 0 to a root cos 2 theta r dr d theta. We have got 2r in this integral. On integration it becomes r square. So it becomes integral theta is equal to 0 to pi by 4 r square to be evaluated at 0 and a root cos 2 theta d theta. Or it becomes a square into integral theta is equal to 0 to pi by 4 of cos 2 theta d theta. Integration gives a square sin 2 theta by 2 to be evaluated at theta is equal to 0 and pi by 4, or the value becomes a square by 2. We can discuss another application of double integrals, that is in determining mass of a plane lamina. If mu is mass per unit area of a plane lamina occupying a region R of the xy plane, then double integral over the region R mu dx dy or double integral over the region R mu r dr d theta gives mass of the lamina. The first integral is the area, is the mass given in Cartesian coordinates, and the other one is given in polar coordinates. Let's now discuss problems on determination of mass. First one, find the mass of a plane lamina bounded by y is equal to x cube and y square is equal to x. If mu or mass per unit area is equal to k into x square plus y square, where k is a constant. We notice that y is equal to x cube and y square is equal to x. These curves intersect at origin and also at 1, 1. So the region of the lamina R can be described by x cube less than or equal to y less than or equal to root x, 0 less than or equal to x less than or equal to 1. Also given mu is equal to k into x square plus y square, where k is a constant. So required mass now becomes integral over the region R mu dx dy. Or on substituting for mu, we get k into integral x is equal to 0 to 1, integral y is equal to x cube to root x of x square plus y square dy dx. Now we can integrate with respect to y. Fine, because y has got variable limit. So on integrating with respect to y, we get k times integral x is equal to 0 to 1 of x square y plus y cube by 3 to be evaluated at y is equal to x cube and root x dx. Or it becomes k into integral x is equal to 0 to 1. When we substitute the limits, we get x to the power 5 by 2 plus x to the power 3 by 2 divided by 3 minus x to the power 5 minus x to the power 9 divided by 3 dx. On integration, we get k into x to the power 7 by 2 by 7 by 2 plus x to the power 5 by 2 by 3 times 5 by 2 minus x to the power 6 by 6 minus x to the power 10 by 30. These are to be evaluated at x is equal to 0 and 1. Or it becomes k into 2 by 7 plus 2 by 15 minus 1 by 6 minus 1 by 30. On simplification, we get 23 k by 105. Of course, whatever be the appropriate unit that we can write. Let's now discuss one more problem on determination of mass of a plane lamina. The problem is like this. Determine the mass of a circular lamina of radius b if the density of the material at any point pxy is proportional to the distance of the point from the center of the circle. What is the problem given here? A circular lamina of radius b. What is the density? How is the density given? If we consider the density at any point pxy or the mass per unit area at any point pxy, it is proportional to the distance of the point from the center of the circle. Without loss of generality, let us take origin as the center of the circle. So, the circle can be represented by x square plus y square is equal to b square. When we take origin as the center of the circle, its distance or the distance of the point pxy from it becomes root of x square plus y square, or mass per unit area or density can be taken as mu is equal to k times square root of x square plus y square, where k is a constant, or in polar coordinates we can write it as kr. Now the region of the lamina R can be described in polar coordinates as 0 less than or equal to r less than or equal to b, 0 less than or equal to theta less than or equal to 2 pi. So the required mass becomes double integral over the region r mu dx dy, or in polar coordinates double integral over the region r mu r dr d theta. Substituting for mu and writing the limit, we get k times integral theta is equal to 0 to 2 pi, integral r is equal to 0 to b, r into r dr d theta, or we have got r square here. Integrating with respect to r, we get r cube by 3. So the integral becomes k times integral theta is equal to 0 to 2 pi of r cube by 3 to be evaluated at 0 and b d theta. Substituting the limits, we get k b cube by 3 into integral theta is equal to 0 to 2 pi of d theta. Integral d theta is theta. Substituting the limits, we get 2 pi. So finally the value of the integral becomes 2 by 3 k pi b cube.